The transition to electric arc furnace steelmaking demands scrap. While EAF production is growing by 4% annually, the global supply of clean prime scrap remains flat. Steelmakers are forced to rely on heavily contaminated post-consumer material. Hidden inside this recycled mix are copper and tin from automotive wiring and electronic waste. Because steel is continuously recycled, these impurities compounding with every cycle, creating a physical Tramp element time bomb. These elements are metallurgically noble. When they enter the melt, their chemical affinity for oxygen is lower than iron. They completely resist standard oxidative refining. Because copper and tin cannot be burned away or slagged out in the furnace, they bypass traditional scrap gate checks and embed themselves into the final product, silently eroding the profit margin of the green steel transition. The metallurgical damage occurs after the furnace. It is triggered downstream during hot rolling at temperatures exceeding 1000 degrees Celsius. This diagram illustrates the hot shortness mechanism. Above 1000 degrees, surface iron oxidizes into scale, forcing liquid copper to concentrate beneath it. This liquid film penetrates the exposed austenite grain boundaries, destroying microstructural cohesion and causing catastrophic intergranular cracking. This flowchart demonstrates how microscopic defects cascade into macroeconomic losses. Surface cracks cause immediate yield loss, which drives up the cost of poor quality. This directly inflates carbon intensity, increasing CBAM tariff exposure, and subtracts millions from EBITDA. Testing for these elements after the steel is cast is reactive and costly. To prevent hot shortness, Tramp elements must be identified and neutralized before the scrap crosses the melt shop doors. This graphic outlines an AI-powered scrap quality stack. By deploying predictive modeling and computer vision, plants move intelligence upstream, characterizing and optimizing scrap chemistry before a single electrode fires. At intake, computer vision and LIBS sensors scan scrap, identifying copper and triggering automated ejection. Downstream, ML prediction engines, trained on 115,000 historical heats, analyze the mix, calculating exact blend ratios to keep Tramp risk below the critical 0.15% threshold. This eliminates the need for conservative guess blending. Operators no longer have to over-specify expensive primary metallics like DRI or HBI just to dilute unknown scrap, protecting raw material margins on every heat. Catching hot shortness before it happens is a direct lever for ESG compliance. Preventing cracked coils eliminates energy-intensive remelting, driving down the volume of CO2 generated per sellable ton. That carbon efficiency translates into financial protection. Lower emissions intensity insulates EAF producers against international regulations, mitigating exposure to the €75 per ton EU CBAM tariff. This dashboard brings these metrics into a real-time executive view. Scrap quality is a board-level risk, and tools like the Tramp Risk Index and automated economic impact tracking provide the visibility required to govern it. These digital tools allow plants to scale metallurgical wisdom across the entire production line. Leaders who integrate AI into their scrapyards will diffuse the Tramp element risk, ensuring product quality and market dominance as the industry transitions to electric arc furnaces. The solution to the Tramp element crisis is an AI-driven predictive intelligence stack deployed directly at the scrap gate, rather than a revised procurement contract. This schematic details the physical architecture. In Phase 3, hybrid YOLO V5 convolutional neural networks visually scan high-speed conveyors to identify and isolate the insulated copper wiring and non-ferrous components that traditional magnetic separation misses. Moving to Phase 4, XGBoost regression frameworks ingest that visual signature, along with inline telemetry and historical heat profiles. This computes the exact trace element chemistry curve before a single electrode fires. By calculating the precise minimum dilution of DRI or pig iron required to keep the melt safe, the algorithm eliminates the need to over-specify expensive primary metallics to cover the margin of error. Because algorithms do not natively understand phase kinetics, these tools must be physics-informed. Metallurgical science must govern the digital parameters to enforce strict thermodynamic boundaries and guarantee defect prevention. This infrastructure is already operating at scale. The £7 million ADAPT-EAF project, partnered with Imperial College London, is actively deploying federated learning to optimize EAF models across multiple plants without exposing proprietary raw material data. This diagram maps the executive economics. Predictive chemistry stabilizes the melt and drives higher yield. That directly drops the cost of poor quality by eliminating cracked coils, scrapped heats, and unnecessary remelts. Processing zero remelts pulls down total energy consumption. That efficiency shrinks the carbon intensity per sellable ton, directly reducing CBAM tariff exposure while securing premium export market access. A focused pilot costing $300,000 to $800,000 cuts Tramp-related reject rates by 50 to 90%. For a mid-size plant, that recovers up to $20 million annually, delivering a payback period of 6 to 18 months. This executive dashboard tracks the exact financial outcomes. Predictive scrap blending operates as a highly lucrative, zero capex alternative to constructing massive primary iron complexes to achieve the same quality baseline. Deploying this advanced data architecture does not require halting current production. This playbook outlines the phased implementation. Month 1 focuses on baselining historical Tramp element variations to quantify true defect costs, while simultaneously extracting 3 to 5 years of existing heat logs to build the machine learning training set. Months 2 and 3 advance into active control. The plant installs intake sensors, deploys a CNN camera array for a single-grade pilot, and connects the optimization system directly to the PLC for automated execution at scale. Clean data infrastructure must be built before the AI is turned on. Executives must evaluate scrap quality not as a procurement footnote, but as a fully governed, board-visible performance metric. Artificial intelligence does not replace the metallurgist, it amplifies their domain expertise. Plants that master this operational synergy will turn scrap quality from a structural liability into a strategic driver of enterprise value.